research that, first of all, it's competitive that in the sense that you make it and you consider it interesting for yourself. Another thing that your colleagues and peers are excited and jealous that they didn't start the same thing earlier than you. And third thing is that you are getting awards and finances flowing from that. So if you look secrets, I think sound did connect. So purple sphere connected us.
Who connected?
I wonder if it's Braden.
Is he not going to be here today?
I don't know. He asked for the link today.
Yes, he asked for the link today. But he should have a microphone. So
He sounded
the requirements from federal agencies are posted freely. There are secrets. And research that has theory component, criteria, and upper and upper. I was really looking what were they requesting. Theory meaning computational chemistry. So they explicitly tell just blindly run single point structure. You need connection to experiment. So you need something that is not yet in the domain of public and commercial software. We need something exciting. So for your research projects, you may want to do this sharp edge comparison. So you can start thinking of your projects right now and doing some preparational steps. But I will spend several meetings, or maybe parts of the meetings, telling about projects and how they can be arranged. And now, very briefly, last time it was offered here in DSU, there was a really good in-class project by, you know each other, and seniors and juniors from different years. Zach Uretz from Inorganic Group. So what he did, it was catalytic has exposed and then reactant bombards this reaction center, experiences reaction, and then two products release. So it was molecular dynamics. If you are well versed in Gaussian, you may imagine doing the same thing by just scanning potential energy surface for single reaction coordinate. But this is good auxiliary thing. But you know that potential energy surfaces are multidimensional, and if you try, instead of scanning it statically, you explicitly model kinetic energy, it can naturally deviate from path that you think is best and select some opposite pathways. So it is more realistic. And for molecular dynamics, force field molecular dynamics doesn't help because it doesn't have bond breaking information. So we need to do up initial molecular dynamics. And so what we did here for field doesn't work. Here we are not doing any of molecular dynamics in the single point. And the Gaussian software, it has these options, but they are not the best possible. Another piece of software that we will spend our third chapter on is intentionally designed for evolution molecular dynamics. It will enable your projects to the next level of competitiveness. So you may count on me supporting your research ideas. So if you have some projects in mind, you can maybe start doing something. But it is, I would be very happy if some of you will comment. My project is done. I am ready to defend my project today, and I do not want to sit in the rest. I had several classes like this in mind, and I was taking this opportunity. But it needs another piece of software that skills that we will be coming through. This is helpful thing, but it will about at the end of the whole April, we'll be in the labs, we'll be doing projects. Does it satisfy your curiosity about organization? Okay. So if you do not see me there are some subjects that we share with each other practically related because in the lab we were doing last night form check of CHEM476. That's a summary of the flows doing changing the isolation surfaces, and then we did realize, we did focus our attention on the fact that in some intermediates, in some unstable radicals, and in very large amount of metal-organic complexes, charge and multiplicity are not zero entity or something different. And if you do it, you need to add letter U to the method because of U HF, and then the result gives you two sets of orbitals, one for spin up and the other for spin down. And the letter U stands for unrestricted, and you see that numbers do not coincide. So same number of orbitals will have different energy and different shape of orbitals identified if you were visiting the lab. What were we doing in the workshop? State of determinant. And here is very rough and especially holographic flowchart of what we're doing in the Hartford session in this chapter. So the goal is to get total energy of multi-electron system at low cost. This is possible only with concept of spin and Slater determinant. The most important part of the Hartford theory is so-called mean field concept, when the rest of electrons exert an average force on the remaining electron, polarization. Today we are going to get a concept of variation theorem, which is so simple that in most textbooks it is explained in one way. I have a feeling of being stupid. I was skimming through and suddenly realized that I do not understand something. Because if there is something important, it is typically explained in several lines. But you just swallow it, no, what was it? And then you start looking back. So we'll spend at least 20 minutes on it. And if time allows, we will go to concept of exchange. If not, we will do it next time. Then the last thing will be flowchart of the algorithm, how this stuff is doing. Another thing that I didn't mention is the hierarchy of data of variables, and it's also very brief and swallowed in most explanations. So we need multi-vector wave function, but it is source layer determinant is composed of molecular orbitals, and molecular orbitals are composed of linear combinations of atomic orbitals. Some people do not get it from the first time, including me. So it is what we saw. We removed the part of molecular Schrödinger equation related to nuclear freedom. We have the rule how to construct the determinant, and here the concept that we started to believe in that another electron, it comes to the place where there's less density of the first electron or the last electron. So they interact, repel each other, and therefore form some distribution. Also, we were playing, how do we call this game?
He-Man or Wheel of Fortune, basically.
Fortune?
Wheel of Fortune.
Fortune wheel, okay. So, for expectation value, and we used this fortune wheel expectation value for it may be carving name with a nail on a glass.
We're in ancient Sumeria. He's using clay.
So, electron-electron interaction is operator that acts on at least two electrons. And we did reduce it to a hybrid concept, that hybrid operator that acts on one electron through making this partial average. And this is the last equation where we stopped last time. So instead, temporarily, whenever possible, we try to forget about, look, well, I see you read on something ridiculous. And you're looking not at me.
We heard a phone vibrate on the
Sounds different.
same.
Oh, you recognize who is it by sending signal?
Yeah.
So the person doesn't answer by voice, but you hear some oscillating software.
Mm-hmm.
Braden, you are not a secret for us anymore. Oh, you know, in airports there are some toys, like scientific toys, voice changers that make your.
He said anonymous.
Whenever possible, for simplicity of lectures, we forget about Slater and anti-symmetry, although we know that we should. So if we have oversimplified Hartree product, simplest multi-electron wave function as a product, which we need to solve Schrödinger equation for, we can split it on two equations. One for orbital of first electron, another for orbital of second electron, where they will have kinetic energy and interaction with ions, and field exerted by the rest of electrons to our electron of interest. Okay. This is a set of equations, but we do not have an algorithm for solution. So it's still complicated. We just, if you know the solution and plug it in, it should be correct thing. But we know that we need to find simultaneously them too, and we need to update the forces that they exert on each other. This is the longest explanation of variation principle I found. So the variation principle is often connected to principle of minimum of energy. If it is something more general, but we are simple guys. We take care. We care only about Schrödinger equations and energies. So if we know exact wave function, if we know that it does exist, we know that it is minimum of energy, then, and we know that it is not changing, then any update to the shape of wave function will increase the energy. So if you want to sound fancy, if you take functional derivative of total energy in respect to variation of wave function, you'll find that you'll find a minimum. I do not see any ways to make it longer, but it is a key concept that later rolls into more complicated and advanced mathematical things that will help us to solve this two or much more equations. So in this notation, if this is true wave function and this is something modified, the energy will be bigger. And this is not a surprise. It is how we find expectation of energy, right? Bracket operator inside. And just in case if we do not know who provided us wave function, we may want to normalize it once again. If you're not sure if it is not the trusted part. So, and if you add a little change to the wave function, then the energy is expected to be bigger. So, what does it mean, variation of wave function? Just little change, little perturbation, little wave. Like we had something with a ground state, minimum, centralized at some point, and we had a lot of things set. So if we get wave function with more fringes, it is expected that it will give bigger energy. So if you want to be rigorous, we can record it this way. So expectation value for ground state wave function is always smaller than expectation value of any other function that is obtained by adding or subtracting something. This is not number, this is distribution. Function is distributed in space. I promised 20 minutes, but I think I'm done. Any questions about variation principle? Doesn't sound unnatural in nature. How can you see which consequences can you imagine of this principle, which looks so natural that we do not want to even to prove? Again, let's look back on who we are and what is our goal. Maybe not globally, but in this course, in this meeting. We do want to find multi-electron wave function and then find its conversion. We can split molecular Schrödinger equation in several little equations, but we still do not have procedure to solve that. We already declined diagonalization of big multi-electron models because if you see for big dimensions, so it should be some truth. And suppose that we are doing very silly way of applied math solution of problems. There is a lot of methods based on throwing a dice or finding random numbers. So suppose that you guess arbitrary wave function, and then you add arbitrary random numbers at left, at right, at different points, and you compare original wave function and the one with random changes. Whichever will give lesser energy will be our next candidate for the wave function. Then repeat. Take the one that came from previous step, again throw in a couple of random spikes, and see if the wave function will maximize or minimize. And then select whatever gives lesser energy, and repeat until the energy stops minimizing. This will work based on the minimum of energy principle. This is just not the optimal algorithm. How do you know at which spatial areas you want to add your random addition? But in principle, one can do it. We just want to do something more elegant and more efficient. So the is there a chance to share content?
In the Call disconnected.
Well, apparently
Huh?
he's had his microphone
Call
muted.
disconnected.
Oh,
Call disconnected, but can
Mine
you
did it
just
after
project
you texted
the
him.
screen to?
Well, he said he's
Just
had his microphone muted since he jumped on.
that
Yes,
was
he's had
the
one too.
recording.
Maybe it was not exciting enough.
He said that he couldn't hear anything when he had headphones in, and he also had his microphone muted. So
Okay.
But it was him.
yeah, so it was him.
So this theorem is of practical importance for us. So we will vary wave function, we will change wave function until we get in. Great, thanks for joining that.
Maybe.
So I'm going to, we are done with this concept of variation of theorem. No one objected, it means that everyone is happy. Anyone wants to vote against? No, so everyone supports this theory. Now, the next concept, and again, you may always ask yourself, why I am sitting here, why I'm spending so much time. I wonder as well. The Hertzog in textbooks is explained in like 1 page. I never saw it be very long, but it's better that we chew it several times from different sides, so we get better and longer memories. So, what are your molecular orbitals that you love so much?
Homo and Luma?
Well, it is semantics, it's their names, but one of them is active again. Last night in the lab, when I asked him this question, what are orbitals, he gave best possible answer. So it's distribution of electrons in space, wave functions. Right? But how do you think they are composed? How are they made? Right now I'm trying to get answer on things that were not in the class, but you through your intellectual activity may guess, or from your experience may get right answers.
Coulombic attractions and light repulsions.
This is principle how they are obtained, is a procedure, the principle of interactions, but formally how they are recorded, how the data are saved. When we were plotting orbitals, we were converting form check file into cube files, which are just set of data. They are fat files, or maybe 100,000 bytes. And the form check is smaller even than the single orbital. So it prompts us that molecular orbitals save not with all amount of data for each point of space. They are encoded much denser. So, and the answer is that it's something natural that you always knew. Molecular orbitals are superpositions, which means summation of atomic orbitals. Right? If you were doing molecular orbitals in organic chemistry or just in very introductory chemistry, you have this SPD hybridization.
Or ML theory.
So there are different atomic orbitals that mix together and form molecular orbitals. Right? So here is this idea, we're just trying to bring in the nomenclature. So, independent of what our background chemistry or physics, we agree that molecules are composed of atoms, ions. R capital, I index of ion. And we need to run this index to take into account of all atoms that compose the molecule. Now, at each ion, we have set of atomic functions. Atomic functions depend on the position of electron, right? And position of electron in hydrogen atom, it counted from the origin, from the so for single H atom, we have origin at 0, and then we have position of this electron, right? And then you get this function. But here the origin is traveling. Whatever our atom is, the origin is shifts, right? So for atom number, for different values of I, there will be different set of atomic orbitals centered at different origins. Different origins. Which letter would give us index of, will give us atomic orbitals? This strange Greek chi. And I was just trying to go along with several textbooks. So this chi is A, atomic orbitals. Okay? You know that atomic orbitals have 4 indices. Principal, orbital, magnetic, and spin. I'm so tired. Let's encode them by now. Just to save time, encode this letter A encodes M, L, and C. Otherwise, it will be too long to write. Even if you are not taking notes, still, it will be long to watch. Or index for atomic orbitals centered at ion number IK. And then each atomic orbital contributes to molecular orbital with weight coefficient. Expansion coefficient. Means some of these coefficients are zeros, some are a little bigger than zeros, and they tell at which percentage atomic orbital contributes to molecular orbital. So it's superposition not only different quantum number orbitals on single atom, but those also run through different orbitals on another atom. So there could be special overlaps of orbitals centered at different atoms. Make sense? So this is molecular orbital. And it does depend only on R, lowercase. So it's one electron object. We look into a multi-electron wave function for big molecule, and orbitals hold just one electron and depend on 3 Cartesian projections. So what you draw and what you will be drawing in the next homework is this stuff, where J is number of orbitals, homo, homo, or something. Sketch. I would call it hierarchy. Or subordination chain. So the goal is total energy, right? And it is what you get upon your run Kharchev. If we are users who tell, hey, we are not technicians, we do not need to know how the car drives, I just want to be transported. Black box. So if we practice this blind use of software, then we just need to take care of the input and output. So input is set of atomic coordinates, that we covered in the first chapter and in the molecular modeling presentations. And output is total energy. Right? And this is black magic box that converts a set of atomic coordinates into total energy. If someone annoys you and asks, like, explain what Hartree-Fock theory is, it's a black box that converts coordinates into energy. It doesn't show how the things work, but it is correct. And not any computational chemistry method can be described this way. Now, what is inside this black box? As soon as you specify positions, you may immediately set of atomic orbitals or basis states centered at each ion. Then, from somewhere, right now we don't care from where, but one is getting set of expansion coefficients. And by merging expansion coefficients with atomic orbitals, one gets molecular orbitals. In fact, when you are looking at your form check, MCTK, it contains this data, which are much more complex. And when you plot molecular orbitals, you merge this and convert it into discretized finite differences form, cube file. And then, if you do have this orbital in either this or this group, you can practice your knowledge about Slater determinant, take all of those orbitals that are occupied, you just count. You order them energetically and count number of electrons occupied. And then you plug it into the Slater determinant, and you do have your multiple two-wave function. And then you find the total energy. Make sense? I would agree with myself that it is correct, but it doesn't help us to solve equations. So again, it is very mathematical in the sense that it is correct, but it doesn't help. So we do not know how to find those, and we may ask ourselves what we are allowed to modify in this chain, in this hierarchy of data. You will not be surprised, and you will see connection. I'll tell that we are going to use variational theorem to vary something in this list. It was the reason to offer this theorem. Now, what can we vary? Can we vary total energy? If we know that it is for really existing molecule, for given geometry, there is only one minimum correct energy. Can we change atomic orbitals? Can we vary atomic orbitals? Does Schrödinger permit you to change his hydrogen atom orbitals? Well, he's not alive anymore, so he doesn't care. We can't change them. But equations will be violated. So those are very well-defined mathematical concepts. They're specified by charge of ion, and we can change them. Those are very clear now. And the expansion coefficients is the thing that we can change. And those two are not quite independent. So, do you have any objections about this logical statement? You do not consider it logical. So, we do want to find multiple atomic wave function, and we do want to vary something. The positions of atoms are given to us. We are not varying. We are not optimizing geometry. We have provided geometry. Atomic orbitals cannot be varied. But expansion coefficients, and we cannot vary Slater determinant. This is also a concept that how we go from molecular orbitals to the function. Slater, his alive friends will not permit us to modify this procedure. Procedure, no. So the only thing that we can, if you want to find correct wave function, the only thing we may modify are expansion coefficients, the weight coefficients, how atomic orbitals contribute to molecular orbitals. The rest is set in stone. Although we do not have any solution, but we do not have too much freedom. So from this point of view, we can set up another definition of Hartree-Fock theory. So it is a way to vary molecular orbitals until you get correct energy. Not the overall wave function, but more specifically, vary expansion coefficients of molecular orbitals. You just change them, and you may submit random or not random numbers to expansion coefficients in a cycle until, through variation of theorem, you get minimum of energy. So it's not hydrogen fluoride. It's Hartree-Fock. Another definition: vary and O until E total. I don't know if it is written up abbreviation. Until total energy is achieved. Okay. I think those are two main concepts that we were not deriving anything. We were just discussing. But the rest, which will be, there will be some other, is rest on this foundation. So if you want to get through Hartree-Fock theory, we need to believe in variation of theorem. And for practical reasons, we need to find an algorithmic way to modify expansion coefficients of how molecular orbitals are constructed of atomic orbitals. Any objections to this statement? Okay, I'm going to briefly introduce or glance through the material that will be more appropriate for next meeting. But since it will be online, I don't know how successful it will be. So I better give some heads up so that you know what to expect, and even connection will be not very sufficient. So those are all words. And the variation will be formulated in forms, so all self-consistent procedure. So until, what is self-consistency? We have a set of equations. We know that if you have this one of them equations for orbitals, we know if you have all orbitals found correctly, these equations will be satisfied. But we don't know this orbitals. So, and we know that forces and potentials that act on depend on whatever we believe is solution. So one needs to iteratively repeat, find some intermediate solution, find force or whatever potential that will act on the electron, resolve it again, plug it in, and so it's like a snake eating its tail. Self-consistent. Okay. It okay. Self-consistent procedure. So with bigger eyes because it's very surprised at this activity. And you have also seen in the last two equations of previous meeting that these equations for one electron orbital look like Schrödinger equation. But the thing that stays in a position of Hamiltonian operator is not a Hamiltonian of overall molecule. It's something similar, but it is different. And since it is a Hartree-Fock theory, instead of Hamiltonian, it will be Fock operator. So F. Same as Schrödinger equation, but F instead of H. So Alyssa was asking how to call these equations last time. Maybe Fock eigenstate equation. Okay. How do you find total energy if you know your molecular orbitals? First, you construct your multi-electron wave function in the form of Slater determinant, right? And then you apply your main principle of finding expectation value. You use Bryan cap, right? So if you have two electrons and you don't care about all chemical only electron interaction. So SD was especially a good abbreviation when I was in South Dakota. So it is Slater determinant. I don't know how to relate it in North Dakota, but Slater determinant is multi-electron wave function, Bryan cap. And if it is only two electrons, we practice it. First, second, first, second, first, second, second, first, right? And because it is Bryan cap, we have star, 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 nothing, nothing, nothing. And you have interaction between electron in position 1 and position 2. And we have integration because it is convolution. Are you happy? Maybe, but you do not know why you shouldn't be. What are the consequences? So it is a way to find energy of electron-electron interaction. Electrons repel each other. Therefore, their energy is always positive, right? You don't want to keep me back in the state. No one objects that electrons repel. And Coulombic interaction of repelling electrons is positive. You can sign on this, and I can catch you on signing it. Now, it's fine if you do it. Now, the electrons are antisymmetric. They obey Pauli, therefore their wave function is minus. So if we open these brackets, there will be two types of terms. Half of terms will have positive sign for repulsion, and half of terms, is cross terms, you have negative sign. So there are terms in Coulomb interaction that have negative term. So they, how to say chemically, stabilizing, minimizing energy. So there is a part of Coulomb interaction that lowers energy. How to say negative, negative. I don't know how to say attractive pulse of repulsion. Maybe it would be the best. Attractive part of repulsion. Right? I regret that I didn't collect your signatures. So, which terms will be positive, which negatives? So, this and this will be positive, this and this, one, two minuses are positive, and cross terms will be negative. Surprised? A little bit. No? So, the first term, if they are, if you take only those terms which are positive, so first, position 1, orbital 1, position 2, orbital 2, position 1, orbital 1, position 2, orbital 2. So this is canonical, standard, intuitively clear repulsion of electron densities. Right? Repulsion of electron densities. And if you are lazy and want to give just one word, we will call it Coulomb. Because it agrees with our intuitive expectations of Coulomb interaction. Now, if you take cross terms, so position 1 orbital 1, position 2 orbital 2, and here position 1 orbital 2, position 2 orbital 1. They are swapped. Right? If because of antisymmetric nature of multi-electron wave functions, this swapping occurs. You didn't object when we discussed it earlier. And now we are bound by Slater determinant. I cannot do anything. So, and this Slater determinant has these negative terms. When the arguments of orbitals are swapped, or arguments are kept, and indices of orbitals are swapped. And this will have negative. So if you swap order of orbitals, exchange them, the energy of Coulomb interaction becomes negative. And therefore, one calls it exchange. Exchange is a stabilizing part of electron-electron interaction. So this is the main difference in Hartree Fock. The Hartree theory has everything as in Hartree Fock, but it doesn't have this exchange term. Therefore, in predicting properties of real molecules, it was given too high energies. They were unstable. And if you include this term, they are more stabilized and more correct.
I'm looking for yellow.
Yes. Okay, so meeting is done. Thank you much for stopping by. Have a safe trip if you're traveling somewhere. And I look forward to present this subject in more details online if it will be allowed to. But the number of lecture will be number 13, which gives me a little suspicion.